Okay, so this section 4.4 is all about rates of change in polynomial functions. And I'd ask you, if you want to save your life a little bit, I'm going to let you in on a little secret that can help you verify your answers, but don't use this in tests. So when you have something like 4x squared, you're going to discover that the rate of change has a formula that is 8x. And what happened there? The 2 went down here, multiplied the 4, and it reduced by 1. Boom. 8x will find the rate of change in any spot of x for this graph. Now that's called a derivative, and that's something you learn in calculus, and it's simply the instantaneous rate of change, sorry if I spell it wrong, for any graph using a formula, because you will consistently find this pattern. Let's have a look at something. The rate of change formula is f of x plus h minus f of x over h, isn't it? And you'll also see it in this format, a plus h, where a is any spot, but it's the same thing, all over h. Those are all the same, and they're the same as slope, delta y over delta x. It's just they've reduced delta x to the difference of delta x, and they just call it h. So if you don't remember how to do this, this is a very important part of functions, and you should go back and review instantaneous rate of change, because it directly leads into calculus. And it's a lot easier if you learn it now. But let's pretend for a second that we're talking about x squared. Now I told you that x squared, you would reduce the 2 down and just come up with 2x as a formula. Let's put it into this and solve it for x squared, as if instead of f of x is equal to x squared. So wherever we see the x here, we're going to replace it with x squared. Let's have a look. So really, we're talking about, and remember, f of x plus h is equal to this when we're talking about f of x equaling x squared. It is not equal to this. That's because whenever you take an f of x situation and you've changed what f of x is, you insert the whole thing wherever you see x. Okay, so keep that in mind. So that means this part here is actually x plus h squared. And I'm just going to focus on this right now. So we're talking about this part right here is x plus h squared. When I expand that, it's clear I get x squared plus 2xh plus h squared. That's a very simple expansion. Correct? Correct. Now, what's f of x? Well, we've just discovered it here, so we have to subtract f of x, which is x squared. Notice that these two things cancel out, and you're left with 2xh plus h squared. Now, if you don't understand cancellation, it's all being divided by h. If you don't understand how cancellation works, that I can cancel one h in each of these things, you can always take an h out of this, and you're left with 2x. Instead of refactoring an h out, you're left with 2x, because that h is gone now, plus h, because one of the h's is gone. It's quite clear now that this h is multiplying these two things and divided by itself so that it's canceled out. So you're left, ultimately, when we do this for x squared, with 2x plus h. But remember what we're looking for. This is at the limit as h approaches 0. Same with both of them. So when h approaches 0 or becomes 0, it's clear it's just 2x. Now, we couldn't do that in the beginning because you can't divide by 0 up here. We had to find a way to cancel out. And that's all derivatives. But notice we're left with the formula I said we'd be left with. X squared, the derivative formula, is 2x. That means if I want to find the rate of change when x is 2, I can just plug it into this derivative formula and discover it's 4. Now I can do the whole process for this here the long way between 4 and 4.001. Right, it's actually 4.001. And minus, it would be like 8.000 something minus 8. And you can do the whole process and discover that you will indeed come out to 4. 3x squared, let's try it for 2x cubed. Now, according to me, the 3 would come down, you'd multiply the 2, you'd get 6x, and you reduce the thing by 1 squared. If you do it in a formula and you expand it and you do the same thing we just did, you will discover that you're left with 6x squared. I'm only telling you this so that you can verify your work instead of, because it's very tedious to do the f of a plus h minus f of a divided by h over and over and over again. I also would encourage you to grab your Desmos and punch in the formula and just call it h of x, or just call it rate of change, IR, and call IR is equal to f of x plus h minus f of x, all of it divided by h, and then you can just set your h to equal 0.001. You can add another line here for an expression, and you put that up top, and you can just even call this rate or r or something like that. Now it's saying, well, we don't know what f is, but it will know what f is when you put in a formula, x squared. Now this means that if I want to find the rate of change, and I've set my h at this, for 2, I can just put in the 2 here. And it's going to spit out, and actually I'm just going to put it in like this, and it's going to spit out the number. Notice that for 2, I said before it's going to come out as 4, and sure enough it comes out 4. If you have Desmos set up like this, so long as you know what you're doing in a test, you should do a few by hand, but after a while you won't want to do a million by hand. So this is a fantastic little tool, and maybe I'll put it in the comment section as something you can just tap on. Okay? Let's get to the book. The book says, it starts you off with a normal graph and a table of values, and it starts asking you certain things like find the rate of change in 1997 to 2005. So that's just a average rate of change. So you would take 1997 here. These are the y values, so you subtract y2 minus y1 divided by x2 minus x1, and they're just getting you used to doing average rate of change right there. And you'll get your answer, and they'll walk you through it. And that just means between that period, there was roughly a period when people are growing faster. Oh, I see. Then they're taking the instantaneous rate of change for those 2 years to see if the population has been increasing faster over time or not. And this is actually a technique that is used in statistics, census, biological studies, studying populations of animals, because you want to know if your environmental protection systems are helping the population you're aiming at. And just keep in mind that all instantaneous rates of change, because we're going to get into polynomials, right, are simply taking a tangent line, or a slope, essentially. That's what a tangent line is, at any point you're interested in. And it's just measuring the slope of that green line. So we can see it's very steep there. We can see it's not steep at all here. We can see it's positive slope here. We can see it's negative slope here. And all that should make sense to you. And that's all instantaneous rate of change is. It's saying, if I were to draw a straight line at the spot I'm interested in studying, what is the slope of that straight line? That's all it is. That's all rate of change is. So if you know how to do slope, you know how to do calculus. Okay? It's just using the little tools and techniques that take a while to learn. All right, continue on. And then it goes through discussion. And it gives you a couple examples. Between 2 and 5, find what happens in this graph, and this is a cubic. You can even punch this into Desmos. So let's take that as an example. X minus 3 cubed minus 1. X minus 3 cubed minus 1. And they're interested in between when x is 2 and x is 5. Well, this is fantastic. What's the difference between 5 and 2? 3. So my h is 3. So I can say that I'm looking for between f of 2, f of 5, and f of 2. And it even punches it out for me. So this is going to give the average rate of change between those 2 points, just as it did here. So you can see that when you have a tool like this, it's very useful because it does average rate of change or instantaneous rate of change. Depends what you want to do in the formula. However, I would strongly suggest you know how to do it by hand. Okay. Then they do it graphically, and they show you why that's true, and they show you a slope, a triangle, and then you're drawing a straight line between that triangle, and you're finding the slope. And then they're saying, you want to use different tools. The graph ball is shown, estimate the instantaneous rate of the point 20. So that's way down here. And one thing you're also going to learn from graphs is that the slope at the top, right here at the peak, is going to be 0. And the slope at the bottom of these things is going to be 0. So it's going to be a very useful way of finding the peaks and the bottoms of graphs, which in science is also very useful. So understand that there's a purpose to these things, and there's a reason, and it's a good way to study. Then they will run you through how to do instantaneous rate of change again. Okay, let's go to the questions. If you don't remember how to do instantaneous rate of change, pull up your YouTube and just say, how do I do instantaneous rate of change? And there will be an excellent person to walk you through it. Consider the graph shown. This is a bicycle, and his elevation relative to sea level. So that means the x-axis is sea level, and here on the y-axis is how far he is up hills from sea level. First 20 seconds of the race are shown, so that means the x-axis is in time. You'll find the x-axis, again, is often the independent variable, and time will often be on there. That's because time marches on no matter what. On which intervals will the tangent slope be positive? Okay. That means when will I have a slope that's going up like this? It's clear the slope is going up here, up here. It's clear it's going up here, up here. It's clear it's going up here and up here. So if I'm going to draw a block between where it's going to go up, and the peak realizes when it turns around goes down, that's a block that's going up. From the bottom of this hill to the peak of this hill is when it's going up. From the bottom of this hill to the peak of this hill is when it's going up. And you can see that there's clear time intervals. From 0 to 2, it's going up. From 4 to 7, maybe. Yeah, it looks like 7, it's going up. From 11 to 16, it's going up. And even here, right here, from 19 to 20, it's going up. And those time intervals you can easily see at the bottom of the x-axis. Keep in mind that each square here is 2 seconds, not 1. So always read your graph. On which slope will be positive? When will it be negative? Well, it's clear that the other side of the hill, going down, the slopes will be negative. From here, it's going down. Here, it's going down. And here, it's going down. They're just trying to remind you when is a slope negative. And I won't do the time intervals, but it's the same method. You find the top of the hill and go down to the bottom of the hill. That's when the slope is negative. Right? And it says, when will it be 0? Well, at the top of the hills, the slope is flat. Try to remember that horizontal lines are when things are flat. And on a side note, when things are vertical lines, they are not. You cannot measure the slope. That is because the delta x here is 0, and you cannot measure delta y divided by 0. So vertical lines don't have a slope. But horizontal lines, the delta y is 0. It's not going up, and it's not going down. And delta x is the distance it's traveling here, so it will be a number. And 0 divided by any number is 0. That's why horizontal lines have a slope of 0. Okay. That means horizontal lines will exist at any peaks. And don't forget, any bottoms. So it's clear the horizontal line exists here, 16. Exists here, 1. It exists here, 4. It exists here, 10. And exists here, 19. Those are all the horizontal lines. If I circle the peaks, it's there. Actually, 4 is wrong. It is right here at... Oh, no, 4 was right. That's a bottom. Here, 10 is a peak. And here, we should have had... Did I miss 16? Yeah, there's 16. That's a peak. So it's clear at 1, 16, and 10, there's peaks. And at 4 and 12, and I forgot this one here, 19, there's valleys. What do the slopes tell you about the elevation of the bicyclist? Well, the positive slopes tell me he's going away from sea level. The negative slopes tell me he's going towards sea levels. In other words, he's going up a hill and down a hill. Consider this function. Determine the average rate of change in each of the following intervals. So this is just saying, there's my delta x from 4 to 2, which is a difference of 2. So my delta x is 2. What happens when I plug 4 into this formula? I get 4 minus 2 squared, which is 4, times 3, which is 12, minus 2, which is 10, which means my biggest value is 10, minus my 2, 0 times 0, minus 2. What is 10 minus minus 2? It is plus 2. What is 10 plus 2? It is 12. What is 12 divided by 2? It is 6. So his rate of change, assuming they haven't given us any units, but let's say y is meters and x is seconds, he is changing at 6 meters per second between that interval. And it also helps to note what kind of graph this is. This is a parabola, isn't it? What's the vertex? The vertex is at 2 minus 2. So is it downward facing or upward facing? It's positive 3 here. It's upward facing. So that means we're dealing with something here that has a 2 minus 2. The point we just took from 2 to 4 is from 2 to here. And it had a positive slope of 6. This point here is from 2 to 6. Is going to be even higher up the parabola, and I can tell it's going to have an even bigger slope. This point here, 4 to 6, is from this point here. It's going to have an even steeper slope. Let's try this too. What's the delta x here between 6 and 2? Well, it's 6 minus 2, which is 4. So that means the bottom number, delta x, is going to be 4. What is the value of 6 when I plug it in? 4 squared 16 times 3 is 48, minus 2 is 46. So you get 46 minus, I already did the 2 early, I came out with minus 2. So minus 2. Minus 2 is plus 2. So you're talking 48 divided by 4, which is 12. So now it's changing 12 meters per second between that interval, twice as steep. What about the next interval, 4 and 6? Well, remember that we already calculated 6. The delta x is no longer 4, it's 6 minus 4, which is 2. Now we just need to calculate delta, or f of 4, which we did before. It's 2 squared times 3, 12 minus 2, 10. So it's 48 minus 10, which is 38, divided by my delta 2 of this, which is 19 meters per second. We can see, as predicted, the slope between 4 and 6 is very steep. The slope between 2 and 6 was, I forget what we came up with now, 12, and the slope between 2 and 4 was 6. You see the slope's getting steeper and steeper, and the numbers are getting bigger and bigger. Estimate the instantaneous rate of change between 4. Okay, try to remember, but between 2 and 4 was 6, and between 4 and 6 was, what did I say, 18? If I take the average of those, so from 2 to 4, it's this slope, and 4 to 6, it's this slope. If I take the average of those, I'm looking at 24 divided by 2. I'm looking at 12. 12. Now, let's look at the rate of change that I discovered between 2 and 4, which was exactly, 4 is exactly in the middle of that. I discovered that that was also 12. So the average rate of change between 2 and 6, and there's 4 there, was 12. And the average rate of change, which I think was 19 actually, was, because I forget what we got, 48 minus 10, 38, it was 19. And then the average rate of change between, if I average 6 and 19, I get 25 divided by 2. I get 12 and a half. So it's safe to say 4 is around, got to be around 12 and a half, maybe to 13. If I was to use my derivative trick, or even if I was to put this in the derivative calculator that I constructed, x minus 2 times 3, was it? Minus 2. And then I take the instantaneous rate of change for 4, and I set my h at 0.1. Oh, look at that. I got let me make sure I got, oh, it's cubed here. It should be squared. There we go. It's 12. It's actually 12. So my first average was even better, and that was taking the rate of change between this point, 2 and 4, or I think that was 2 and 4, and 4 and 6, and then averaging those two slopes. You can see it's actually 12. Okay, let's get back to it. and this was square. That's why I got the wrong answer first. Estimate the instantaneous. I did 12. Explain whether the rate of change in fx cut in part in A and B are positive. Well, as explained, we are dealing with this parabola, and this point here is 2 comma minus 2, the vertex. Since all the changes we were taking was 2 to some other number, we were always going on the positive side of this slope. Had we found the rate of change over here between, I don't know, 1 and 3, we would have come up with a slope of 0, which would not have told us anything about this graph, and it's very deceptive. So you can see that sometimes taking average slope won't give you what's going on with this graph. So it's really helpful to know what the graph is doing. State an interval in which the average change of x will be negative. Well, there's lots of intervals here. Anywhere to the left of 2x. So if I take it from 0x to 2x, the slope will be right here in red. Be roughly, very roughly, here. If I take it, for instance, between 1, which is about there, and 2, that's the slope right there. And I didn't even quite get it on the line on the graph, but there. That's average rate of change between 1 and 2x. It's negative. State the coordinate point where the instantaneous rate will be negative, or the instantaneous rate of change. That would be any point on this side of the vertex, anything where x is smaller than 2. Not equal to 2, because at 2 here, the tangent line, the slope will be 0. But anything to the left of 2 will produce an instantaneous rate of change that is negative, because the slope is going down from left. You always read a graph from left to right, from x left to right. Since time is marching that way, the slope is marching that way. Okay, let's look at the next one. So they're just running you through your pages. These first 4 are from last year, actually. You should have all these skills from last year. So here they're giving us this graph on the left, so I'll just try to copy it. And I'll skip number 5. Okay. Okay. Consider, first they just start with a graph right here. Consider this graph. Estimate the instantaneous rate of change when x is 2. Now I'm going to let you into that secret. Remember, what's the derivative of that? 3x squared. What's the derivative of this? Minus 8x. What's the derivative of this? Well, x is to the 1. When it goes down and multiplies the 4, it's 4. X to the 0 is 1. So I'm just left with plus 4. If I plug 2 into the formula, I get 2 squared, which is 4, times 3, which is 12, minus 16, plus 4. So 12 plus 4 minus 16, it will be 0, which tells me that this is the vertex of this graph. And if I look carefully at it, always study a graph. What can be factored out? What can be factored out? An x. And I'm left with x squared minus 4x plus 4. What's the factors of that? Well, it's x minus 2 and x minus 2. That's x minus 2 squared. Which means with my knowledge of cubics, especially since this is a positive, I can tell it's going through 0, 0. And I can tell it 2 comma 0, because this is squared, it's going to go up, bounce down, and bounce up again. Since the question they're asked about is when x is equal to 2, I already know that that's a bounce back spot, and I know the slope will be 0. So visually, graphically, I could have figured it out as well. I just had to hope this was factorable. Now, what does your answer to part A tell you about the graph at x is 2? It tells me that that's the spot, one of the spots, because this is a cubic. A cubic can have a maximum of 2 max and mins. It tells me that either a min or a max. Now, because of my knowledge of the graphing, I was able to figure out it's a min. But otherwise, I just have to guess that that's, since it had a slope of 0, and we were taking an instantaneous rate of change, that was going to be 0. But estimate, they want us to estimate it. So here's what you would do to estimate it. You're going to be taking this twice, all divided by h, and it's going to be, everywhere you see x, it's going to be x plus h. Right? So it would be, instead of 2 here, let's say my h is 0.0001. It's going to be x plus h. So it's going to be 2.001 cubed. 2.001, and I'm going to make my h 0.001. So it's 2 zeros. 2 zeros. Cubed minus 4 times 2.001 squared plus 4 times 2.001, which is actually an easier one. It's 8.004 minus, so remember that this minus is going to apply to everything in there. So let's keep my minus separate. 2 cubed, 8, minus 2 squared, which is 16, plus 4 times 2, 8. I can see that this is all 0 because it's adds up in the brackets to 0, so minus 0. So really I just have to figure out what this is, divided by that. So I take out my calculator and I go 2.001 cubed, and I put it in my memory. And then I have to subtract 2.001 squared times 4. I didn't get the zeros in there. 2.001 squared times 4. And I have to subtract that. So I'm going to add that as a negative to my memory. And then I'm going to take 8.004 and I'm going to add that to my memory. And then I'm going to recall my memory and I'm going to divide it by my h. And I can see I get a very tiny number, 0.002, which I can sort of guess, well, that's pretty damn close to 0. That's how you do it the long way with instantaneous rate of change. You can also throw it into decimals with this tool. X cubed minus 4x squared plus 8x. Was that it? 8x? I think that's it. 4x plus 4x. Then I can, since I'm looking for a 2, I could just plug in 2 here, and sure enough, it's going to give me, this time I'm taking a much smaller h, so that's why it's approaching 0 even closer. And it gives me a good idea. It also shows me the graph, and I can see why that's 0 there. But you can use this tool, you know, to verify your answers, or you can do it by hand. You can do the little cheat method I gave you, but use the tools at hand. You'll learn faster. What does your part A tell you about the graph function? Yeah, it's a min or max. Sketch a graph of x, find the zeros, so that's why I did that. And then they're just giving us a graph, right? This is clearly a cubic, and it's clearly a cubic that has a max or a min. But notice they give you the x-intercepts, right? So that means I already know that this is going to be a times x plus 4 to get to that minus 4 here. X minus 2 to get to that plus 2 here. And x minus 4 to get to that plus 4. To figure out the full formula, I would need any one clean point. So look at there. I got a clean point right there, 0, 8. So that means when 8 is y, x is 0. So when it's 0 here, 4. When x is 0 here, minus 2. When x is 0 here, minus 4. Minus 4 times minus 2 times 4 is minus 16 plus 32. So that means 8 is equal to 32a, which means a is equal to 8 divided by 32, which is the same as 1 over 4. which means I can now come up with this graph. 1 over 4, x minus 4, x minus 2, x plus 4, and sure enough, I have the graph in the book now. Calculate the average rate of change between 4 and 5. So now that I have the formula, I can use the formula, but clearly they just want you to use the graph. So they want you to do average rate of change. So let's find 4. Here's x of 4. And let's find 5. Ooh, we can sort of see it's right there. And y is 7. So it's 5 comma 7 and 4 comma 0. If I take my delta y, 7 minus 0, and I take my delta x, 5 minus 4, I get 7 over 1. And I can tell you my rate of change is 7 between those 2 points. That's the drawing a secant. That's the slope of that secant. I can also do it over here now that I have the formula. I can say what's the difference here between 5 and 4, and the difference in x there is 1. Yeah. And it was f of 5 and f of 4. And it's giving me 6.5. So I might have gotten the formula wrong. Let's see if I got the formula. That's pretty close. Unless that y-intercept isn't perfect. Let's try the formula again. I'm saying a, when y is x, is going to be equal to x plus 4, which is 4, x minus 4, which is minus 4, x minus 2, which is minus 2. I got 16 times minus, I got 32, oh sorry, 32a. No, I got it. It's equal to 8. So a is equal to a quarter. So that should be it. So that means with my graph, I'm doing a rough, I'm not quite getting the 5. So I didn't quite get the accurate 5 over here. And according to my graph, the actual 5 is not 7, but 6.75. And that shows you how the formulas are much more precise than visual, so making slight error. You can also, to get that idea of the slope, is you could just take a line and draw it through the points that you think, and then you can use any squares here to construct a right angle triangle to get a better, more accurate measurement of the slope of that secant. Estimate the coordinates of the point on the graph whose instantaneous rate of change is the same as that found in part A. So we're looking for something that's still going to be that. Well, I can say it's the halfway point between 4 and 4.5. I'm going to say it's the halfway point. So that would be x is equal to 4.5. And that means my rate of change will be the same. Let's go and use my tool and find the rate of change between the rate of change at 4.5. So that's 4.5 plus h minus f of 4.5 all over h. And sure enough, pretty close. 6.68 instead of 6.75. But it's not bad. Let's see if f 6.6 does it. 4.6. No, too high. So 4.5 is pretty accurate. Let's try 4.4. Yeah, 4.5 is the closest thing. And that's because if I take a look at this, this is an important bit of knowledge to have. If I take an average rate of change between these 2 points, let's just say like there, the halfway point here will pretty much match that average change. See, if I just make a parallel line, put there, that's going to be roughly, oh, I'd say I had to also lower it a bit. So I'm trying to draw a parallel line to that other one. Say that's about it. And I'd say that fits on a graph, a little bit higher, a little bit lower, somewhere around there. And that means at this point here, I would find my x. So I can see it's roughly about 5. And the secant I happened to take were 4, 2 roughly. It's about 5.5. And the halfway distance between that is indeed 5. So you can see that when you take an average rate of change between two x values, it's usually the average between those two x values that will give you a similar instantaneous rate of change. And we learned that last year, actually, in functions. Continuing on, I'll try to speed up. Sketch a graph. Estimate the coordinates. Yeah, we just did that. Okay, so now we're going to get into the real stuff. 5. Now, this section, and you'll find instantaneous rate of change, it's a bit torturous because there's so much calculating error. For each of the following functions, calculate the average rate of change between 2 and 5, and that square bracket, so I used to use squiggle bracket. It's actually square bracket, means you're including it, which means 2 is smaller or equal to x is smaller or equal to 5. So they're saying this is a straight line, right? Well, straight lines are always easy because the slope, no matter what point I take or between 2 points, that slope is always going to be the same, m. And the m is right in the formula, 3. So I don't even have to take it. So since I'm looking for average rate of change, I will. What's the difference in x here? 3, always. So that means my delta x is 3. No matter what. And what's my delta y? Well, I got to plug in the 2 here. So I get 7. So 7 is one of the things. I plug in my 5 here, which is 16. 16 minus 7 is 9. And the x, delta x was 3. And look at that, 3. But, of course, this is just a line. That's going to be the slope no matter what. Lines are the few things where the rate of change is the same no matter where you take it. Not so for parabolas because the curve keeps changing. Not so for cubics because the curve also changes directions. This is a rational function. Try to remember, actually I should go to b next. So this is a parabola. If you factor it, it's very hard. Actually, it's minus 2. So it's 3x minus 2, and I believe x minus 2. So 3x squared minus 6x plus 2x, and then minus 4. Now it's got to be 2, 6 minus 6x squared. It would be a number that multiplies out to 3, but adds up to 4, so it's not factorable. No, 3 and 1. So it's going to be 3x minus 1 and x minus 1. There you go. 3x squared minus 3x minus 1x, that's minus 4x, minus 1, or plus 1. So there's the factors of it. So it's clear to me that this is going to be a normal cubic, and it goes through 1, 0 here, and 1/3, 0, which is this mark. Between 2 and 5, I can say that it's going to be over here, 2 and 5. So it's going to be quite steep. Okay, now I can use this, or I can use this. It doesn't matter. Just remember my delta x is going to be 3 the whole time. So when I plug in 5 here, I get 15 minus 1, 14, times 4, 28, 56. Oh, 56 is one of my y2. When I plug in 2, I get 6 minus 1, 5, times 2 minus 1, 1. So it's minus 5. So I get 51 over 3. If you don't know what I did there, I happen to know I'm looking for my delta y, which is the difference between 5 and 3. First I took 5 and I put it into the formula to come up with my y1. Then I put 3 into the formula, 2, should be a 2 because it's x2, into the formula to come up with 4 times 3, 12, minus 8, 4 plus 1, 5. Then it's 56 minus 5, that's my delta y for 51. And my delta x, as I always mention here, is 3 because it's the same delta x over and over again. So 51 over 3 is roughly, I'm not going to do it, it's roughly 16 point something, 0.3, something like that. And yeah, it's 48, and then it's 3 divided by 3. I think it's 0.1, 48.1 repeating. sorry, 16.1 repeating. And so that's my rate of change for that slope. Now, what about C, this one here? Try to remember what that looked like. That's going to look like this. Here and here. And between 2 and 5, the slope is going to be right like that. So I know the delta x is 3. And if I take 2 first, or 5 first, I get 1/5 as my y2 minus, take my 2, 1, 2 as my x1. Go back and revisit slope if you can't remember what this is. For me to subtract this, I have to put this and this over the same number. I can cross multiply, and I get 2 over 10 minus 5 over 10. 2 over 10 minus 5 over 10 is negative 3 over 10. So I get my delta y is negative 3 over 10. All of that divided by delta x, 3. Well, 3 is the same as 3 is over 1. When you're dividing fractions, you simply take the first fraction and multiply by the reciprocal of the denominator fraction. And now I get minus 3 over 30, which is the same as minus 1 over 10. Why is my slope minus 1 over 10? Well, it's clear. The slope is going down there. The slope is going down. It's also minus 1 over 10 is a very small slope. It's minus 0.1. It's quite clear that that slope is quite flat at that part, almost totally flat. Because as this graph goes to the right, this line gets flatter and flatter, but never perfectly flat. So that makes a lot of sense. What's this graph going to be? That graph is clearly a parabola, and the parabola vertex is 0.7. It also faces downwards. So that means that's going to be the peak, and between x value of 2 and 5, we can expect a negative value. If I put 5 in there, I get negative 25 plus 7, so that's negative 18. If I put 2 in there, I get negative 4 plus 7, which is plus 3. But remember that you're always subtracting your delta y's, so that becomes minus 18 minus 3, which is minus 21. I'm always dividing by the same delta x, 3, so it's clear my slope here is negative 7, which makes a lot of sense because it's clear this slope between these two numbers, remember the parabola is going to go down like this, is going to be very steep, very steep. That's my tangent line, which is, or sorry, I should actually say secant line between 2 and 5. Now you can throw these into Desmos and discover the same thing. What about this one? Well, try to remember your growth curve. Growth curves are going to look like that. And they're also going to have very common points. Oops. They're also going to have very easy to figure out points. For instance, I know that when x is 0, y is 1. So 0, comma 1. I also know when x is 1, y is 2. I also know when x is 2, y is 4. So that's the point of interest that we're starting at. And so I can jump right to 5. When x is 5, y is 2 to the power of 5, which is 8, 16, 32. So when x is 5, y is 32. So taking a secant line between those two, it's clear that my graph is going to be very positive, and very steep. 32 minus 4 is the delta y, and delta x is always 3. 32 minus 4 is 28, divided by 3. And that means we're going to get roughly 9, just before 9. 9.333333. So that's the slope, and it's positive. It makes sense why it's positive. And this last one, you say, well, what the hell's that? That's y is equal to 9. What is y is equal to 9? What does that mean? Well, x is equal to any number is a vertical line, and y equaling every number is a horizontal line. And what's the slope of any horizontal line? 0. So the average rate of change, just like any line, is the slope, which is 0. For each of the functions specified, estimate the instantaneous rate of change of 3. 3 isn't quite in the middle of it, but we can go for it. First of all, instantaneous rate of change for lines will be the same no matter what. So if the answer here is 3 and 0, because rate of change, whether it's average rate of change or instantaneous rate of change, is the same. In this graph, I remember that we have quite a steep parabola, right? And it went through, I forget what it went through. I think it was 1 2/3 or something. So that means that 3 is going to be somewhere around here. If I take 3, I'm going to get 3 squared, 9 times 3, 27, minus 12. 27 minus 12 is 15, plus 1, 16. So I'm going to get 16 as my f of x, my f of 3. So that means 3 comma 16. That means if I'm going to take an instantaneous rate of change, I'm going to take 3.001. So I'd have to take my calculator, and everywhere I see x, I have to put in 3.001. So the first x is squared. This is for an h of 0.001. So the first x is squared. I get 9 times 3, 27, minus 4 times 3.001, which is equal, and then plus 1. And then I have to subtract the y value I found, which was 16, and I have to divide it by my h. And I discover 14.03, so it's probably 14 is my instantaneous rate of change. I can also get an accurate graph and do the same thing for 3, f of 3. And discover the same thing. I can also take that little trick I told you about and get 6x for the first derivative minus 4, and then just plug in the 3. 3 times 6, 18, minus 4 is 14. So no matter what, I can see the 14 is the rate of change. You can also finally, if you have a graph and you know where the point 3 comma f of 3 is, right there, you could take your graph, and it helps if you make it a little bit wider. There we go. That helps a little bit. That helps even more. Actually, it doesn't help too much. Well, it might. And you take a nice screen image, and then you take that, try to get your tangent, try to draw a tangent that perfectly cuts that line. Not quite. Okay, something like that. And then you simply draw a triangle on some clean points, like here, roughly, and here, and measure. Well, I got a delta y 2, delta x of, that's 9, and that's 2, so delta x of 7. And I got a delta y of 0 all the way up to 100. And 100 divided by 7 will give me the slope of this tangent. Now keep in mind this is going to be the roughest estimate, but the fastest estimate. So you can take 100 and divide it by 7, and you get 14.28. So you can see that you get more air here, but it's a very fast way of doing an estimate. And since they say the word estimate, I would suggest that that's not a horrible way to go. Mind you, you have to have a pretty good, accurate graph of it. Okay, what about here? Okay, so I know it's very flat, and I don't think the graph would reveal too much information for me. So I know I'm dealing with 1 over 3.001 minus 1 over 3, all divided by 0.001. So I'm going to let the calculator do that. 1 divided by 3.001 minus 1 divided by 3, which is 0.333, and equals. So I get this whole thing, and I'm going to divide it by my h. And I get a negative 1 slope, negative 0.1 slope, and here I get this. And that's not too bad. Remember that our actual answer before was 1 over 10, negative 1 over 10. If I put this equation here, and this is the nice thing about this formula, I can even set this to a. Let's call this a. And then I can just set my a to whatever number I'm interested in. And there we go. There's the accuracy. So that makes me think I did the calculations before incorrectly. But there you go. There's your dot. And I should just do a3 of a. So it's always going to put the dot we're interested in. And there you go. That's the actual dot. And you can even get good at drawing slopes of those dots. For instance, the slope of this line is going to be equal to my rate of change here, negative 0.01111. And all I have to do is do y minus my f of a times this x minus my a. And it will suddenly draw me a tangent line. And that's true no matter what slope I draw. Now, why didn't it do it properly for me there? Oh, I had to do f of x. Sorry, f of x. No, still not right. Oh well, I'll get it eventually. Anyway, you can see here now I've got it in here, and I've got a is equal to 3, and it's going to give me my slope for that line. So no matter what, you can put in whatever equation you want. You can put in the actual instantaneous rate of change equation. You can assign your a, you can assign your h, and you can even verify it by having it label that dot. What I was trying to do, and I failed miserably, is I was trying to make a line. It would help if we called this something. Or if I assigned it down here. R is equal to the same thing. Ooh. Oh, radius, no. Okay, I'm just going to call it big R. Yeah, there we go. And then I can do a line that takes my R, x, but I have to do x minus the a and y minus the f of a. There. This draws a tangent line, essentially. And no matter what I make my a, it will redraw a tangent line. And this is an excellent tool. I'll probably just save this with the description so that you have it. I would urge you, though, to know how to do these things by hand. Because, and actually I can just put this one up here. I don't have to write it twice. Because you need to learn how to do it on a test without these tools. But these tools make your verification a lot easier. All right, continuing on. What about this one? Okay, when x is 3, I get minus 9 plus 7, so I get minus 2. Then I would have to take 3.011 squared plus 7, subtract 2, and divide it by 0.001. Okay, let's try that. By the way, we're doing this one here now. I should put it with the equation that we're doing. So when I take 3.01 squared, and then I have to make it negative, then I add 7, I get that. And then I have to subtract 2 that I found in the for f of 3. Then I have to divide it by my h. Well, I got the wrong thing there. And I discover an impossible number, so that's when you know you made an error. So, verifying that 3 is 9, minus 9 plus 2 minus 2. Oh, it's minus 2. So I'm actually going to add the 2. So 3.01 squared, negative plus 2. And a negative 2 is adding 2. So I get that. And then I've got to divide it by, I got the first part wrong. This here shouldn't be negative 7. It should be like negative 2. So clear it all. 3.001 times itself, negative, add 7, equals. There we go. Now I'm going to add 2. Then I'm going to divide by 0.001. And I'm going to get my slope, negative 6. So sure enough, for this thing here, it's saying it's negative 6. And we already figured out that it goes through 0, 7 and faces down. So you can always put it into this equation. You can make your A 3, make your H as big, small as you want. A is equal to 3, not A. And there, it'll give me my instantaneous rate of change here, and it'll draw me my tangent line with this here. And it will label the point I'm interested in. And you're using essentially the formula straight from the book. You just have to understand what they each mean. And it all makes sense. And it's what we found before. I found it algebraically, and you can find it with your tools. And then finally this, we discovered it was a very steep thing. And what you would do is you would take 2 to the power of 3.001 and subtract 2 to the power of 3, which is 8, and all divided by 0.001. So you can see the formulas can be quite quick as well if the f of x is simple. So 2 to the power of 3.001 equals minus 8 divided by my h. And I get 5.54 as the rate of change, which makes sense because at 3 it's somewhere around there. So if we put 2 to the power of x here, and we're looking for 0.3, there's 0.3 there. You can see the tangent line in purple is less slope than the average rate of change we found before. And there we go, it even prints up the rate of change for you, which is the instantaneous rate of change formula using h of 0.001 and a as the spot on the graph. A is simply the x value. The book likes you to start thinking in terms of a, because a can represent any point on the graph instead of saying x. And it gets clearer as you go why that's the case. Graph this. They're saying graph it. I'm going to actually take both questions here and move them up. Okay. So it's saying graph this by finding its zeros. It's clear x squared can come out of both, and I'm left with x minus 2. It's clear this is a cubic. It's going to bounce through 0, 0. It's a positive coefficient. So we're talking about something that comes up, bounces at 0, 0, and then immediately goes through 2, 0. But it bounces here. It should be touching the graph here at 0, 0. So that's 2, 0. It'll go through because of this. When this is equal to 0, x must be 2. That's how you get it. Okay. Use the graph to estimate where instantaneous rate of change is positive, negative, 0. Okay. So it goes through 0, 0 and bounces back. So that means everything to the left of 0 will be positive. Everything here will be negative. This is going to be roughly, not quite, at x is equal to 1 because it's between 0 and 2. So roughly down here at 1, you'll get a bottom of the slope. So that means the whole slope is negative between 0 and 1. So let me put this in proper terms. In red, I'm going to draw where the slope is positive forever. And in green, I'm going to draw where the slope is negative. So that means, in numerical terms, the slope is positive when x is smaller than 0, or when x roughly is bigger than 1, not quite. And the slope is negative between 0 and 1. Now that's not quite right. You will learn in future textbooks how to find the exact minimum. And that's when this slope, or in other words, the instantaneous rate of change for this thing is equal to 0. And you will be able to solve it. In other words, you will be able to solve when does x plus h cubed minus 2x squared cubed. Well, let's use the formula that I factored out. When x plus h minus 2 minus this x squared, x cubed minus 2x squared, plus hx, and it's all got to be brackets, over h, when is that equal to 0? And you won't have to use this complicated thing, because when you expand it, you'll discover tons cancel out. And you'll just be able to discover exactly when the graph is flat. If I put this into Desmos, it's minus 2x squared plus x, I discover the graph points. Let's see, I got that wrong. Oh, did I have it going? No, it's positive x cubed. That's what's going on. So there's the point it goes through. And sure enough, it's going to go through this point. Oh, and you know what did I do wrong there? Oh, when I factored it out, I totally forgot this x here. So let's try this again. Okay, let's take the actual thing, and I missed this x. I can only factor out an x. I get x squared minus 2x plus 1, which factors out to x minus 1 squared. So I had the wrong square. So that now means it goes through 0, 0, doesn't bounce back, comes up and bounces at 1, 0. So now the new slopes in red are positive here and positive here. So I didn't see this plus x over here. So that means when x is smaller than the peak is roughly 0.5 and x is bigger than 1, the slope is positive. And when x is between roughly 0.5, smaller than x, smaller than 1, it is negative, which is this part here. So that's just a factoring error, which shows you that if you rush, you can get it wrong. And the slope will be roughly flat here and here at, so it'll be flat at 1 and it'll be flat here. Now, putting this into the thing, we discover, sure enough, see how it's not peaked at 0.5, it's slightly to the left. You can only get close. However, I can say, when will this equation equal 0? And I wouldn't be able to set it for, actually, you know what you could do instead? You could just slide your a value, there's roughly it, until you get an R0. You can see it's roughly 0.3. It's pretty close there. And this allows you to sort of find your flat points and your maximums wherever you want. Let's make this a little bit wider apart. X minus 2 to show you what I mean. X and x plus 2. Just to give it a bit of hills and valleys here. There we go. Now if I click this, there. It's quite clear that this is going to be the flat point. So you can sort of say, okay, I'm going to just kind of guesstimate. I can see it's going to be around 1. Let's make it 1. Okay, 1.1, 1.2, 1.15, there, 1.16, somewhere 1.55, somewhere around there. So right away, by finding where the slope is 0, I can find my x value of when the bottom of it is. Over here I can see it's going to be roughly the same number but minus. And I can find it over there. Once I plug it in, I can figure out my y value and essentially graph my points. You might say, well, you didn't really solve it, and you'd be right. You'd have to expand everything and solve it for a, because you know your h here. And it would take a lot of algebra, but it's just to show that you could make it, figure it out. Construction worker drops a bolt from a high rise at 320. And it's defined by this thing here. So the height of the bolt, based on the time, is equal to minus 5t squared plus 320. You can see right away that when time is 0, the height is 320. Because when t is 0, this whole thing comes out to 320, which means it either goes up a little bit and then falls. It depends if he dropped it. He drops it. So we're probably looking at like something like this. It's going to hit the ground when this is 0. When's this 0? Well, you set this equation equal to 0. And it says 8 seconds, so probably 8 seconds is when it hits the ground because we're dealing with 0 to 8. Find the average velocity between 3 seconds and 8. Okay, what's the delta x here? 8 minus 3. So the delta x is 5. You just have to figure out where 8 is. So 8 squared, 64, times minus 5 is minus 500, minus 320, plus 320. Oh, that doesn't make sense. Let's try it again. So it was doing 8. Oh, yeah, I am doing 8. So it's 320 minus 5 plus 320, so that it's 0. The height is 0. So it does indeed hit there. So you get 0 minus, what's the height when it's 3? 3 squared is 9 times minus 5 is minus 45, plus 320 is 275. No, 285. If I subtract 345 from that, 320 from that, I get minus 35. So I get 95. No, 75. If I subtract 320 from that, so if I subtract 275, I'm left with 45. So that's right. So that means it's 0 minus 275, which is clearly minus 275 divided by 5, which is 5 goes into 27, negative 27, negative 5 times, negative 55 meters per second. Because when you take a slope of a distance over time, you're going to get a velocity. So that means it is the average velocity between 3 seconds and 0 when it hits the ground is negative 55 meters per second. Find the bolt's velocity exactly at 2. Okay. I'm going to get rid of all this. I'm going to do this. All right, here's the formula. You're going to take an h of just 0.001. And that means your h down here is 0.001. And you're going to take minus 5, and we're looking for time is 2. 2.001, which is t plus h squared, plus 320, minus 5. See, this minus is separate from the actual operation. 2 squared, which is 4. So this comes out to minus 20. Plus 320, which is 300. So it's minus 300. All I have to do is figure out what is 2.01 squared times minus 5 plus 320. So 2.001 squared times negative 5 plus 320 is this. 299.97. It's going to always be very close to your f of x. So I'm going to take minus 300, and I'm going to divide it by my h. And I get negative 20.005, which I'm pretty sure is going to be negative 20 meters per second, which means in that first 3 seconds, it's falling at 20 meters per second. You can do this by putting it into the formula that I gave you. And I'm just going to use x to keep the formula the same. You're going to see the lovely graph. I'm going to make the y go from 0 to 320 so that we can see it. I'm going to make they're asking for 2 seconds, and there it is. And sure enough, it's spitting out my r of negative 20 meters per second. You can also make a copy of this, and I'm just going to alter it, and you can do that old thing that we just figured out, which was that they wanted the difference between 8 seconds and 3 seconds, I think it was, over 5, and that was this secant line. Was it 8? 8. 5. Oh, I see, and it's unfortunate it's taking a here, so I'd have to use the actual values to get the secant line, which is no. Anyway, it won't draw the tangent line for me unless I adjust this formula, and I'm not going to bother. But my point is you can come out with the value that you want. Now let's go back to what I had. And then I'm going to actually take, was I taking A2 minus 26? Did I come out with times 2? Oh, I got my H way too big here. There we go. Then you could actually take the formula that I gave you and say, well, Peter told me to take the derivative of 320 minus 5t. 2, interesting enough, derivatives of numbers don't matter, so I can just get rid of that. I bring the 2 down from the t and multiply it by minus 5, I get minus 10. I lower the exponent by 1, t. Then I plug in my 2. Minus 10 times 2 is minus 20. Oh, it works. So it's a good way of just testing out what you're doing. Onwards. 9. Estimate the slope of the tangent line at x is equal to 1. Find the y-coordinates of the point of tangent. Okay, well, this helps to just understand the graph as well. Always just try to say, okay, I know this graph. It's upward-facing parabola. I also think that if I can factor it and come up with a number that adds up to minus 3, multiplies out to minus 3 and adds up to minus 4, that the numbers might be, yeah, unfortunately it won't work because you're talking about plus and a minus. And since it's plus 3 minus 1, it won't work. So you won't be able to figure this out in terms of its factors, but you do know it's an upward-facing parabola. You could also conceivably factor out the 3 and discover that the vertex x is going to be at 2/3 by completing the square. Then when you put 2/3 into it, you will discover that 2/3 squared is 4/3. 4/9, times 3 becomes 4/3 again, minus 4 times 2/3 becomes 8/3. So 4/3 minus 8/3 minus 1. And you'll discover that this is indeed, what's 4/3 minus 8/3? It's minus 4/3 minus 1. What's 1 in thirds? Minus 3/3. So you get minus 7/3, which is roughly minus 2.33333. So you will discover the vertex is at 2/3, comma, negative 7/3, essentially. And in decimals, and that's just by completing square. In decimals, that's 0.666 repeating over negative 2.333 repeating. So that means it does go through the x-axis because this is clearly below the x-axis. Figuring out where it goes through the x-axis requires a quadratic function formula. However, when x is 1, we now know it's just to the right of this vertex. It's just here. So it's probably below the x-axis, which means we know we're looking at a positive slope. Find the y-coordinate of the point of tangency. Well, let's plug it in. When x is 1, by the way, this also goes through 0, comma, minus 1, right here. So that's interesting. And we could say, okay, find the y-coordinate of the point of tangent. When x is 1, we get 3 minus 4 minus 1, which is minus 2. So we know we're starting below the x-axis. Estimate the slope. Okay. We were going to take 3 times 0.001 squared minus 4 times 0.001, which is minus 4.004 minus 1, minus, and what did we discover is the y here? Minus 2. So it's going to become plus 2. All over 0.001. So if I do 1.01, square it, times 3, minus 4.004 equals minus 1. Then I add 2. I get that, and I'm going to divide it by my h. And I get 2.03, so it's quite clear to me that the slope is going to be roughly 2. If I take my trick and take the derivative of that, 6x minus 4, and plug in 1, I get 6 minus 4, which is 2. It also confirms my answer. Use the coordinates at the point of tangent and the slope to find the equation of the tangent line. Ah, this is a great point. How do you find, let's assume we got 2 as the slope, okay? So, hello? So, let's say we know the slope is 2. What's the equation? It's y is equal to mx plus b. Turns out we don't know the b. We do know the m. It's 2. We do know it goes through a point on this graph, 1, comma, what did we find out? Minus 2, right? Okay, so that means minus 2 is equal to 2 times 1 plus b. So minus 2 is equal to 2 plus b. Bring the 2 to the other side. Minus 4 is equal to b. So that means the formula for this line is going to be y is equal to 2x minus 4. And that line will create a tangent line that touches the parabola right where we want it. Let's use our thing, our little thing that we've already constructed exactly for this, to see if that's true. I think it was 2x squared actually. 3x squared minus 4x minus 1. There's our parabola. Let's click the home button. There we go. There's exactly where I thought the vertex was. There's the point. Remember that we're interested in point at x is equal to 1 here, not 2. That's the point we're interested in. And let's just get rid of this, or unhighlight it, and put in the formula we found. Minus 2x minus 4. Oops. Wasn't minus 2x, the slope was 2x minus 4. Look at that. It's exactly the same as our purple line, right? So we can see that we can find lines of tangents if we know the slope or the instantaneous rate of change, and we know any one point on the parabola, because they will share the same point. That's what a tangent is. They share that one point. And you can construct the formula for the tangent line. Very important to remember that. Number 10, the height of a toy rocket on the ground. So, right away, if this is a toy rocket taking off, I can almost guarantee you that it's going to be represented by an upside down parabola, like this. I can also guarantee you that sometimes they won't care about some sides of it. So sure enough, it's upside down parabola. I want you to factor out t here. Even minus 5t, I'm going to factor out. When I factor out minus 5t, I'm left with t minus 10, which means that it's going through 0, 0 here, and the next time it hits the x-axis is 10, 0. It's also quite easy to see that that means the maximum height will occur halfway between 0 and 10 seconds, or 5. If I plug in 5 here, I get minus 25 times minus 5, which is plus 125. So it's quite clear to me that the height is going to be 5, 125. And I just know that because along the same y-axis of any parabola, the halfway point will be the x value of the vertex. That's how it is for any point. If I know this point here and this point here, the halfway point will be the x value of the vertex every time. Okay, use an average speed to approximate the instantaneous speed of 4. So I can tell you already, I know that's on the way up. So I should get a positive result and quite steep. Actually, it's coming to the curve there, so it won't be as steep actually. And okay, so it's saying average rate of speeds, which would mean I would take from 5 to 3 to get an idea. And then use an average rate of speed to stay at 10. So that's just as it's colliding on the ground. So that'll be its steepest curve, and it'll be negative. And then what's the average rate of speed over the whole interval? So that I can answer right now. That's going to come out as 0, which would be confusing. And it doesn't really tell you much. That all says, okay, well, nothing happened. The rocket never took off. But clearly, it took off and landed, and the average of that trip, in terms of how height changed, that's really what the speed it's measuring. It's saying what's its velocity from here to here comes out as 0, and that's just simply because its height averaged out by the end of that trip. So you're not learning anything from that. So the answer to that will be 0. 10, I can either use it with the instantaneous rate of change philosophy, but they say use the average rate of change. So for the first one, for 4, I'm going to measure the difference between 5 and 3. So 5 and 3, it's obviously the delta x is 2. And I've already got the y for 5. So I'm going to subtract. I need to figure out for 3. So when I put 3 into this formula, I get minus 15 times minus 7, which is plus 105. So I'm subtracting plus 105. 125 minus 105 is 20. 20 divided by 2 is 10. So I'm going to estimate, using those two average rate of change, which is a dot to the right and a dot to the left, that is going to be positive 10 meters per second. That doesn't tell me if height, oh yeah, meters. Now, using instantaneous rate of change, I'm going to take the same formula we had actually because it's useful. And I'm going to say this is going to be, actually I'm going to use this one. For time of 4 is 5 times 4.001 squared plus 50 times 4.001 minus, what did I determine? I didn't determine. At 4, this is minus 20 times minus 6, which is minus 1, what did I say, minus 6? Minus 120. Okay, so I just need to figure all that out, and I have to remember to divide by h, 001. So 4.001 squared times minus 5 plus 50 times 4.001 is equal. And then I have to subtract 120. And then hit equal, and then divide it all by, if you don't hit equal, it'll divide it by h first. 9.995, which is very close to my average change that I took. So 9.995, it's quite clear that it's probably 10. So that average rate I took between 5 and 3 gave me a really good idea of what was going on. Where would not the average rate of change work? Well, exactly in their last question. This average rate of change in the last question doesn't reveal anything. What is the average rate of change of 10? So for this one, I'm just going to use my formula. So I'm getting minus 5 t times t minus 10. And instead of t, I'm going to use x so that I don't screw up my other formula. I'm going to use an a of 10. And it will show me minus 50 for 0, 1. I'm going to make my 0 even bigger. So it's clear that the instantaneous rate of change here is, I'm going to get rid of this drawing here, and I'm going to turn this back on. And it's clear that my instantaneous rate of change, the purple line, is my purple tangent line. And I'm just going to make my y's a little bit smaller. So that I get a better idea of that. I'm going to turn off my tangent line for a second. And it's clear, rate of change was indeed minus 50. I'm going to go confirm it for 4 now. And it's clear, and I'm going to put on the tangent line for that. It's clear at 4. My rate of change was positive 10. You could have also used my cheat method, but you would need the original formula. The original formula, I believe, was minus 5t squared plus 50t. The derivative of that is minus 10t plus 50. If I plug 4 in there, I get minus 40 plus 50, and indeed comes out as 10. If I plug in 10 in there, I get minus 100 plus 50, which indeed comes out as minus 50. So you can see that rate of change derivative is a big clue to what's coming in your future. You don't have to learn that. I'm just trying to help you out in the future. Then they do it a couple more times, but I'm going to have to save this page because I'm getting called, and I'll do part B soon.